Hello, and thank you for coming to this presentation on design verification with Step and Compare for RISC-V extensions. My name is Lee Moore. I've been involved in a number of RISC-V projects over approximately the last 5 years, but recently my attention has been specifically focused on helping our customers and partners with the design and verification aspects of the many chips in which we're helping to achieve the necessary compliance to the ISA and the quality metrics to ensure the RTL has been thoroughly tested. Specifically today, I will be talking about the verification of a vector engine, but before that, let me give a little background of how we got here today. What we are talking about today is using an architectural representation to ensure the fidelity and quality of a microarchitectural implementation. At Imperas, we provide a range of detailed instruction-accurate simulation models of processors and peripherals. In providing an architectural processor model, it is incumbent upon us to describe all of the possible architectural decisions that could be used in a specific implementation, and we call this the envelope model, one which covers all of the possible legal and functional aspects of the specification. When designing a device to conform to a given specification, the responsibility of the implementation team is to produce a design which fits within the functional specification, but more importantly, meets the design goal challenges, whether that be area, performance, power, or any other goal. Our desire is to use the architectural model to ensure that during the design, test, and continuous integration of the RTL, that the functional representation remains within the legal constraints. You can think of this as a highly configurable and powerful assertion and protocol checker. There are many different approaches to hardware DV, including those shown in this list. Each of these techniques provide increasing levels of detail with respect to the comparison data points. We can think of the simplest form of a self-checking test to produce an expected response, to the most complex, such as the asynchronous lockstep compare, where the complete architectural and microarchitectural state is recorded and compared within a scoreboard system. This contains information about instructions, registers, privilege modes, asynchronous events such as interrupts and debug. For RISC-V, a reference model must be able to cover all legal combinations covered by the specifications. Then there is the added complexity of extensibility, including custom instructions, registers, exceptions, and interrupts. More importantly, a simple and correct by construction method of extending the envelope model for those custom extensions. Most importantly, our experience has been that in the real world, the challenges are a little bit more chaotic. There is further dimension to this complexity, which is that real designs start before ratification completes, in which case it's imperative to be able to support combinations of ISA revisions from draft to ratified and everywhere in between. Let's briefly consider some of those combinations which must be handled by the reference model. Firstly, we have numerous standard extensions. Looking at one of those extensions, such as the bit manipulation extension, we can see it has numerous revisions. And by the way, as mentioned before, in the real world, we have design starts which were initiated at these individual revision milestones. As if this complexity wasn't enough, we also have to consider any subsetting of the extensions. Again, looking at the bit manipulation extension, this is further broken down into support for a number of subsets, to which the reference model must be configurable. I hope that has given a brief introductory glimpse into the complexity and requirements of a reference model for RISC-V design verification. Let's now start to look in a bit more detail at the specifics of the vector extensions. So once again, let's look at the alternates within the vector specifications. And firstly, we have the configurations containing settings for VLEN, ELEN, and SLEN. SLEN configurations were actually only relevant in specifications pre-0.9. Which once again leads me nicely into the fact that the vector specification has also been going through a number of iterations. And as mentioned previously, we have designs which are being targeted at different specification milestones which we have to handle as part of the reference model. We tend to get involved with two types of DV. The first I will call inclusive extensions. This is where a full process of verification is performed, which includes the extension as part of the processor RTL verification. Later, I will describe how we help to verify co-processor extensions. The important aspects of this type of verification are as follows. The reference model can easily be controlled by whatever verification system is used. We have integrations using System-C, System-Verilog, and SpecMan. The reference model can export its internal state in order that the verification system can interrogate the state as part of its scoreboard comparisons to the RTL. And finally, that the reference model can be directed with information which cannot be determined by an architectural reference itself. A good example of this are things like asynchronous events, such as debug and interrupts, and unpredictable register values, such as a cycle counter, which is completely dependent upon the microarchitectural implementation. During the development of the various DV flows, we've been in the process of formalizing the requirement into something we call the RISC-V verification interface. This interface is intended to encapsulate the reference model in such a way that simplifies the integration into a DV framework such as System Verilog. And we do this by providing a control interface to step the model through the instruction execution and allow asynchronous events and unpredictable register values. A state interface is also provided which exports all of the internal state for comparison. And as can be seen in the diagram, we present a view of the GPRs, FPRs, CSRs, and most importantly, in this case here, the vector register bank, which is sized accordingly based upon the vector engine configuration of the reference model. We can now take the reference model and embed that into a full simulation framework along with the RTL which is to be verified. The test bench performs the coordination of execution and comparison of state, generating appropriate warnings and errors where divergence between the two references occurs. A typical test bench execution flow is shown in this state diagram. This is a simplified view of the flow used in the open hardware Core 5 verification test bench, which uses the Imperas reference model to validate a number of their cores, including the CV32E40P, X and S. I mentioned earlier there were two types of DV. Let me describe how we can perform the DV activities of a standalone RISC-V coprocessor which communicates over a bus such as OVI or Core 5 XIF. We're currently involved in a project performing verification of a standalone vector coprocessor connected via OVI. Now, the difficulty this customer has is that they do not have the entire RTL system in place. This means they cannot write RISC-V programs for directed testing, run any of the compliance suites, or use a random instruction stream generator. There is no fetch unit, execution unit, instruction pipeline, or any other components which are necessary to execute instructions and forward the vector instructions to the vector unit. Using the RVVI interface around the reference model, it is a simple task to extract the internal state and forward that state for execution and comparison to the RTL coprocessor whenever a vector instruction execution occurs by the reference model. Thus, whenever a vector instruction is executed in the reference model, the coprocessor performs the same action, enabling the comparison of all the necessary states by the test bench. This approach provides the entire testing of directed, random and compliance, even in the absence of the core processor, which would normally be exercising the vector unit. The final part of my presentation, I would like to give a brief demonstration to show a reference model configured with a vector engine running in the RVVI interface. This particular vector engine is configured as 0.7.1 release with an ELEN of 64 and a VLEN of 2048 with an SLEN of 2048. So let's have a look at what this looks like running under System Verilog. Earlier I showed this slide of how we export RVVI into System Verilog. If we have a look at what this looks like from a software and a hardware perspective, in a software view we can see this instruction about to execute. If I step over that and then take a look at those vector registers, you can see the update to that register for the VAD instruction. And if I let this continue to the end, I'm just going to go and look at all of the waveforms that are produced in the hardware representation. And if I zoom all the way out, let's have a look at the vector registers. I just want to find the first change, which is there. I'm going to shrink that back down because what I want to see is what actually happened at this point. The first thing to note is that we get a notification that a vector instruction is executed on this signal here, and you can see here we've got the VAD instruction for the operation we just saw in the view of the software. And so we can use that information in order to drive the coprocessor in the System Verilog wrapped encapsulation. In conclusion, at Imperas we've worked on many of the DV approaches shown above, but by far the most comprehensive solution is to be able to run an asynchronous lockstep compare environment. This allows the full verification of the synchronous execution units, but with the added benefit of handling asynchronous events in order to ensure that the coverage metrics can be successfully measured and achieved for all of the kinds of cross-covered synchronous and asynchronous events which are of interest to a DV team aiming for a very high standard of performance and quality. Thanks for that, and hopefully we kept to our schedule there. I'm quite happy to take any questions as well.
Fantastic, thank you, gentlemen.